we have looked quite in detail on how to draw a ray diagram for converging lenses and diverging lenses. And we have actually used the lens diagram in order to identify or to determine the characteristics of the image that is formed through these lenses when we change the object distance from the lens. Okay, later we'll do some questions to solidify our concept on ray diagram of lenses. Okay, so lens diagram is good for us to determine the characteristics of the image, whether it being real, virtual, upright or inverted, or magnified or diminished. We have learned that it's the same thing for mirrors as last time. Okay, and again, same with mirrors, ray diagram allows us to determine the characteristics qualitatively, but when it comes to the exact position, exact height, all those kind of measurements, it'll be difficult to determine it just by using a ray diagram. Okay, of course, if you draw a perfectly drawn ray diagrams, then things you can measure the length of the arrow to determine the height of the image, let's say. But that is not the best way of determining this kind of measurements, as there's a better substitute to do this work. We can rely on equation to let us know these measurements. So let us move to the second method, where we use a thin lens equation and magnification. Well, the formula for thin lens equation, it still looks the same. It's something that I shade over here, 1 over u plus 1 over v equals to 1 over f. This is thin lens equation, and the shape is the same, the symbol is everything the same, just that the sign convention, there's a little bit of wording that you might need to change. Okay, then we also have the magnification. This magnification equation is exactly the same like last time. Okay, so for thin lens equation, 1 over u plus 1 over v equals 1 over f, the purpose is still the same. It's still used to relate between the object, the image, and the lens. In this case, the lens is represented by the focal length. Okay, let's look at the sign convention before we move on to talk about this part of the equation. For the sign convention, for u is still at the same like mirrors. So if your object is on the same side as incident rays, then you can get positive u. But if your object is on the opposite side of the incident ray, you can get negative u. I mentioned last time that I can't think of any situation where you have negative u, but eventually after looking through some of the exercises or questions in books, found out that it's actually possible. Okay, let's say for this case over here, you have an image form over here, right? What if you place another lens between this lens and the image? So you place a second lens over here. So the image that is formed here will now be the object for the second lens. But the object is on the other side of the lens instead of on the incident side of the lens. Okay, the light ray here will be forming this image here. And this image here will be the object for a second lens that we put here. But the image or the object of this second lens here is on the opposite side to the incident ray. In this case, the u, if we place our lens over here, will be a negative u. Okay, well, we'll probably encounter this kind of situation later, but it is really rarely found. Okay. So the next one is on V. V, the idea is still similar. If your image is on the same side as the refracted rays, then it will be positive. In this case, our image is on the right hand side of the mirror, and our refracted ray is also on the right hand side of the mirror, so both on the same side, so our V here will be positive. If our V happens to be around this area, then we know that the refracted rays and the image should be on the opposite side, then you get a negative. Okay, so the u and v is still the same as the spherical surface that you learned for the previous subtopic. But for f, the focal length, that's where things get a bit different. But you have encountered this in the first video on thin lenses already. We have learned that converging lenses is also called as positive lenses. So for the focal length, you can just put it as positive if you encounter a converging lens. If it's a diverging lens, you know that the focal length will be negative. So this is by default already. Okay, if you want to ask why this is positive, why this is negative, and that is where our lens maker equation comes in. Our f, whether it's positive or negative, it depends on this equation here. If you remember from mirror, this f over here is equals to r divided by 2. But now when we are talking about lenses, there are two spherical surface involved. Sometimes it's planar, okay? But there'll be two surfaces involved, and each surface might have different radius or curvature. In that case, you have to take into account both of the radius or curvature, and this is the equation that we find out. So this equation allows us to sometimes get focal length that is negative. Sometimes the focal length can also be positive, and depends on R1 and R2, whether it's bigger, larger, positive, negative. Those will influence the sign of our focal length. Then of course it also depends on the medium. In this case, the N here, N material, is the material that makes up the lens. What's the refractive index of it? Then the medium is the surrounding. Most of the case is air, unless you immerse this lens into water, let's say. Okay, so this equation, we will review it in greater detail in the next video probably. Okay, then the next equation, I have the magnification equation. Nothing has changed for magnification equation. The same characteristics. Absolute value is above 1, then you'll be a magnified image. If it's the value itself is positive, then it's upright. The value itself is negative, then it's inverted. Then if your magnification is between +1 and -1, then it's diminished. Okay, it's still the same as mirror, nothing has changed. The formula is also the same. There's a negative sign if you're talking about image distance divided by object distance. So let's try and apply what we learned in the question.